term extended down conductor method isn't explicitly used in NFPA 780. The correct terminology is direct connection method, and it's covered in the 2004 NFPA 780 section 4-7.1.3.1. This method involves directly connecting the down conductor to the grounded object. So, when you're working with a direct connection method, or what was referred to as the extended down conductor, ensure it extends a minimum of 2 feet from the foundation or footer of the mast. When using a copper plate for grounding, the disconnect point between the down conductor and the copper plate should be located where the down conductor makes contact with an uncoated section of the plate. If the plate includes a connection lug or a copper lead wire welded to it, the disconnection point should be at the juncture where the down conductor connects to the lug or the wire. The depth at which the copper plate is buried is important. Regardless of the depth of any underlying rock, a plate should be buried at a depth of 1 to 2 feet in clay soil or 2 feet in sandy soil. If the ground resistance check exceeds 25 ohms for a single copper plate, it is permissible to add a second plate, placing it 10 feet away from the first plate, and then retest the ground resistance. Regarding the length of the ground rod, the depth to which it is driven is more important than its overall length. The ground rod should ideally be driven to a depth of at least 10 feet into the earth or until it reaches bedrock. However, if rock is encountered to a depth of 9 feet below the existing grade, an 8-foot rod driven to that 9-foot depth would be acceptable, provided that the ground resistance tests at less than 25 ohms. The key to effective grounding and lightning protection systems lies in achieving a low resistance path to ground. This facilitates the safe dissipation of lightning energy, protecting structures and individuals from potential hazards. Ground resistance is the measure of how well the grounding system is connected to the earth. A low resistance value indicates a better connection, allowing for a more effective path for lightning current to flow into the ground. A higher resistance value means a poor connection, which can impede the flow of current and potentially lead to voltage buildup and equipment damage. The 25 ohm standard is a common benchmark used to determine the effectiveness of a grounding system for lightning protection. It's based on the principle that a resistance of 25 ohms or less provides an adequate path for dissipating lightning energy safely into the earth. Soil type significantly impacts ground resistance. For instance, clay soils generally have lower resistance than sandy soils. This is because clay particles are smaller and hold more moisture, which improves conductivity. Sandy soils, with larger particles and less moisture retention, tend to have higher resistance. The depth at which a grounding electrode is buried affects ground resistance. Deeper burial typically results in lower resistance, as the electrode is in contact with more stable and potentially more conductive soil. The size and material of the grounding electrode also play a role. Larger electrodes and those made of highly conductive materials like copper can help reduce ground resistance. Moisture content in the soil is a critical factor. Dry soils have higher resistance, while moist soils have lower resistance. This is why ground resistance can vary seasonally, with higher readings during dry periods. Temperature can also affect ground resistance, though to a lesser extent than moisture. Freezing temperatures can increase resistance, particularly in soils with high moisture content. The presence of salts and minerals in the soil can lower resistance by increasing conductivity. However, these substances can also be corrosive to the grounding electrode. The direct connection method is also sometimes referred to as the conventional method. It is the most straightforward approach, involves directly connecting the down conductors to the grounding electrode system. The primary advantage of the direct connection method is its simplicity and cost-effectiveness. It requires fewer components and less labor compared to other methods. One potential disadvantage is that it may not be as effective in highly resistive soils or complex geological conditions. The earth interface transition method involves using a series of interconnected grounding electrodes to create a lower resistance path to ground. This method is particularly useful in areas with poor soil conductivity or where deep grounding is not feasible. It requires more careful planning and installation, but can significantly improve grounding effectiveness in challenging environments. The equipotential bonding method focuses on minimizing voltage differences between different parts of a structure. This is achieved by bonding together all metallic components such as pipes, conduits, and equipment housings to create a common ground potential. Equipotential bonding reduces the risk of dangerous touch voltages during a lightning strike. Proper installation and maintenance of grounding systems are essential for ensuring their effectiveness. This includes regular inspection of grounding electrodes and connections, as well as periodic testing of ground resistance. Regular maintenance helps identify and address any issues that could compromise the system's performance. Adding a second ground plate is a common practice when the initial ground resistance test fails to meet the required threshold. The placement of the second plate, typically about 10 feet from the first, helps to expand the grounding area and reduce overall resistance. The shape and size of the grounding electrode influence its effectiveness. Ground rods are commonly used due to their ease of installation, while ground plates provide a larger surface area for contact with the soil. The choice depends on site-specific conditions and requirements. The spacing between multiple grounding electrodes is critical. Electrodes that are too close together may not significantly reduce ground resistance, while those that are too far apart may not be effectively interconnected. The recommended spacing is typically determined by local codes and standards. Soil treatment involves adding materials to the soil to improve its conductivity. This can be particularly useful in areas with highly resistive soils. Common soil treatment materials include bentonite clay and conductive concrete. A ground grid is a network of interconnected conductors buried in the earth. It provides a comprehensive grounding system that can effectively dissipate lightning energy and minimize ground potential rise. Ground grids are commonly used in substations and other high-risk facilities. Ground potential rise occurs when a large current, such as a lightning strike, flows into the ground. This can create a voltage gradient in the surrounding area, posing a risk of electric shock. Effective grounding systems help minimize ground potential rise. Lightning protection systems are designed to protect structures and their occupants from the harmful effects of lightning strikes. These systems typically include air terminals, down conductors, and grounding electrodes. Air terminals are installed on the roof of a building to intercept lightning strikes. They are typically made of copper or aluminum and are designed to withstand the high currents associated with lightning. Down conductors are used to carry lightning current from the air terminals to the grounding electrodes. They are typically made of copper or aluminum and must be properly sized and installed to handle the expected current. Grounding electrodes are used to dissipate lightning current into the earth. They are typically made of copper or steel and are buried in the ground. The grounding system should be designed to provide a low resistance path for lightning current to flow into the earth. Regular inspections and testing of lightning protection systems are essential to ensure their effectiveness. This includes checking the air terminals, down conductors, and grounding electrodes for damage or corrosion. It also includes testing the ground resistance to ensure that it meets the required standard. Lightning protection systems should be designed and installed by qualified professionals who have experience in this field. They should be familiar with the relevant codes and standards and should be able to design a system that meets the specific needs of the building or structure. The National Fire Protection Association, or NFPA, is a leading source of information and standards for fire and electrical safety. NFPA 780 is the standard for the installation of lightning protection systems. The Institute of Electrical and Electronics Engineers, or IEE, is a professional organization that develops standards for electrical engineering. IEE 142, also known as the Green Book, provides recommended practices for grounding and bonding of electrical equipment. Local codes and regulations may also have specific requirements for lightning protection systems. It is important to consult with local authorities to ensure that the system meets all applicable requirements. Selecting the appropriate grounding electrode depends on several factors, including soil conditions, space constraints, and budget. Ground rods are a common choice due to their ease of installation and cost-effectiveness. They are typically driven vertically into the ground and are available in various lengths and diameters. Ground plates offer a larger surface area for contact with the soil, making them a good choice for areas with poor soil conductivity. They are typically buried horizontally in the ground and can be made of copper or other conductive materials. Ground grids provide a comprehensive grounding system that can effectively dissipate lightning energy and minimize ground potential rise. They are typically used in substations and other high-risk facilities. Concrete encased electrodes, also known as UFO grounds, are installed within concrete foundations. They offer excellent grounding performance due to the large contact area with the concrete and surrounding soil. Chemical ground rods contain chemicals that leach into the surrounding soil to improve conductivity. They can be effective in areas with highly resistive soils, but they require periodic maintenance to replenish the chemicals. The installation of grounding electrodes should be performed by qualified professionals who have experience in this field. They should be familiar with the relevant codes and standards and should follow the manufacturer's instructions. Ground rods should be driven into the ground to the required depth, ensuring that they are in contact with stable soil. Ground plates should be buried at the appropriate depth and backfilled with suitable material. Ground grids should be installed according to the design specifications, ensuring that all connections are properly made. Concrete encased electrodes should be installed within the concrete foundation during construction. Chemical ground rods should be installed according to the manufacturer's instructions, taking care to handle the chemical safely. The testing of grounding systems is essential to ensure their effectiveness. This includes measuring the ground resistance and verifying the continuity of the grounding conductors. Ground resistance testing should be performed using a calibrated ground resistance meter. The test should be conducted under dry soil conditions to obtain the most accurate reading. Continuity testing should be performed using a multimeter to verify that all grounding conductors are properly connected. The results of the grounding system testing should be documented and kept on file. Any deficiencies should be addressed promptly to ensure the continued effectiveness of the system. Effective grounding is crucial for protecting electrical equipment and personnel from the hazards of lightning strikes and other electrical faults. A well-designed and properly installed grounding system provides a low-resistance path for fault current to flow back to the source, minimizing the risk of electric shock and equipment damage. The direct connection method is commonly used because of its relative simplicity. This method involves connecting the down conductor directly to the grounding electrode, typically a ground rod or ground plate. The advantage of this method is that it provides a direct path for lightning current to flow to ground, minimizing impedance and reducing the risk of voltage buildup. However, it may not be as effective in areas with poor soil conductivity or where deep grounding is not feasible. The radial grounding method involves connecting multiple grounding electrodes in a radial pattern around the structure. This method provides a more distributed grounding system which can be more effective in areas with varying soil conditions. The ring grounding method involves encircling the structure with a grounding conductor, which is then connected to multiple grounding electrodes. This method provides a very low impedance path to ground and is often used for sensitive electronic equipment. The mesh grounding method involves creating a grid of interconnected grounding conductors buried in the earth. This method provides a very comprehensive grounding system and is often used for large facilities or substations. The hybrid grounding method combines different grounding techniques to achieve the desired level of protection. For example, a hybrid system might use a combination of direct connection, radial grounding, and ring grounding to provide a comprehensive grounding solution. The selection of the appropriate grounding method depends on several factors, including the size and type of structure, soil conditions, and the level of protection required. A qualified lightning protection professional can assess these factors and recommend the most appropriate grounding method for a specific application. Regular inspections and maintenance are essential to ensure that the grounding system remains effective over time. This includes visually inspecting the grounding conductors and electrodes for damage or corrosion, and testing the ground resistance to ensure that it is within acceptable limits. Any damage or corrosion should be repaired promptly, and the ground resistance should be tested regularly to ensure that the grounding system is functioning properly. Effective grounding is an essential component of a comprehensive lightning protection system. By providing a low impedance path to ground, a well-designed and properly installed grounding system can protect structures, equipment, and personnel from the hazards of lightning strikes. Grounding is the process of connecting electrical equipment and systems to the earth. This provides a low resistance path for electrical current to flow back to the source in the event of a fault, minimizing the risk of electric shock and equipment damage. There are several types of grounding systems, including equipment grounding, system grounding, and lightning protection grounding. Equipment grounding is used to ground non-current carrying metal parts of electrical equipment, such as enclosures, conduits, and motor frames. This provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the equipment. System grounding is used to ground the neutral point of an electrical system. This helps to stabilize the voltage and reduce the risk of voltage surges. Lightning protection grounding is used to protect structures and equipment from lightning strikes. This involves installing air terminals on the roof of the building, which are connected to down conductors and grounding electrodes. The grounding electrodes dissipate the lightning current into the earth, protecting the building and its contents from damage. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that electrical systems are installed and maintained safely. The NEC covers topics such as grounding electrode systems, grounding conductor sizing, and bonding requirements. It is important to follow the NEC requirements when installing or maintaining electrical systems. In addition to the NEC, there are other standards and guidelines that provide information on grounding electrical systems. These include IEEE standards, UL standards, and manufacturer's instructions. It is important to consult these resources to ensure that the grounding system is installed and maintained properly. Effective grounding is essential for electrical safety. By providing a low resistance path for fault current to flow back to the source, a well-designed and properly installed grounding system can protect people and equipment from the hazards of electrical faults and lightning strikes. Proper grounding is not only a safety measure but also a critical component for the reliable operation of electrical and electronic systems. Without proper grounding, stray currents and electromagnetic interference can disrupt the performance of sensitive equipment, leading to errors, malfunctions, and even damage.